Hi everyone, my name is Liang. I come from City University of Hong Kong. I'm going to talk about the work Acclaim. This work aims to improve the user experience in Android systems. First, let me quickly go over the overview of this talk. We found the memory reclaim scheme is inefficient in Android systems, especially under intensive I/O requests. Specifically, we found that there are many page defaults and direct reclaim during application daily usage. We further found that there are two main causes of this problem. First, the size of reclaim scheme is usually too large for Android applications. Second, the background applications keep consuming free pages, even though they do not have the same impact on user experience compared to the foreground applications. This paper aims to improve the user experience under intensive I/O requests. The work name is Acclaim. It includes two parts: a lightweight prediction-based reclaim scheme, LWP, and foreground-aware eviction, FAE. LWP dynamically tunes the size and the amount of reclaim scheme according to the predicted allocation workloads. FAE sees free pages from background applications and allocates them to foreground applications. Experimental results show that Acclaim can significantly reduce the launch latency and improve write performance under intensive I/O requests. Now, mobile devices are everywhere. This figure shows the number of global users. The deep blue line is the number of desktop users. The light blue line is the number of mobile users. The number of mobile users has surpassed the desktop users since 2014. This figure shows the global mobile OS market share. Different color line represents different OS. We can see now 80% mobile devices use the Android system. We know current Linux memory reclaim scheme has been used for many years. Android inherits Linux kernel, and thus the Linux memory reclaim scheme is directly transplanted to Android mobile devices. However, the workloads of mobile devices are totally different from server or PC, which the Linux kernel designed for. For example, their request sizes are usually small, and their foreground applications are more important to user experience. Now let's dig deeper and see how this difference can impact the launch time of mobile applications. So we broke down Android I/O latency. Let's take read procedure as an example. When an application reads a page in I/O stack, the kernel searches the page in the page cache. If cache hit, the access latency takes about 100 nanoseconds to complete. If cache miss, a page fault is generated. In this case, the page allocation will be triggered to allocate a new page. When the memory is full, the Linux reclaim scheme is conducted to free pages. After page allocation, the request is delivered to flash storage. Going through each of these layers contributes to additional microseconds to this read request. Let's see the influence of page faults and reclaim scheme on application launch latency. We conducted this experiment on two popular file systems, F2FS and EST4. Y-axis is the application launch latency. Higher is worse. The blue histogram represents the case that all pages in the page cache. The green one is the case that page fault happened. And the yellow one represents both page faults and reclaim happen. The results show that the page faults take much longer latency indeed, especially when reclaim scheme is triggered. Let's look at these two factors. First, page refault. Page refault happens in three cases. First, when reading a page for the first time. Because the physical memory is not allocated for this page refault happens. Second, when a process reads a wrong address, this process will be killed. Third, when reading an evicted page, this is also called page refault. An evicted page is demanded again soon after, means page thrashing. Page refault can cause page thrashing, and thus it is a key factor that impacts user experience. Let's see the reclaim scheme. There are mainly two reclaim schemes, background reclaim and direct reclaim. Let's see the page allocation flow. It shows how do they work. During page allocation, if the number of free pages is lower than a threshold, the background reclaim starts asynchronously. If there are not enough free pages for system's demand, or the launched background reclaim does not reclaim enough pages in time, direct reclaim will kick in synchronously. Direct reclaim is a heavy cost. The page allocation has to wait to finish. Notably, when the memory is extremely scarce, direct reclaim cannot help either. In this case, background applications will be killed to reclaim free space. In a word, direct reclaim is another key factor that impacts user experience. Now, we know both page refault and direct reclaim impact user experience. We want to evaluate how these two factors performed on real mobile devices. Thus, we run a monitor applications on 52 mobile devices to collect the background application usage information. The survey uses more than 20 smartphone models over 2 months period. The monitor application on our GitHub. You can download it if you are interested. And then we design evaluation scenarios according to the survey. Application combinations used in experiments are listed in the following table. A presents launch and user applications for 5 minutes. 3B plus A means that launch and user foreground applications for 5 minutes when there are 3 background applications, and so on. The experiments use 20 applications, including social media, browser, map, game, news, and multimedia applications. Experimental setup is Huawei P9. Based on these evaluation scenarios, we analyze that above two factors, page refault and direct reclaim. First, let's see the number and the ratio of page refaults on mobile devices. The main y-axis is page refault number. The higher is worse. Orange histogram is the number of foreground page refaults. Blue histogram is the number of page refaults happen on background applications or system. The second y-axis is the refault ratio. The line is the total refault ratio. Refault ratio is the percentage of refault on the total eviction. These results show that both background applications and the memory pressure increase the number and the ratio of page refaults. Moreover, the ratio of page refaults is up to 31%. This means almost 1/3 of evicted pages will be reused. Now, let's see the results of direct reclaim. The blue histogram is the number of direct reclaim. The line is the direct reclaim ratio. The ratio is the percentage of direct reclaim on the total reclaims. The higher is worse. The results show that both background applications and memory pressure increase the number of direct reclaims. You can see the ratio is getting lower when the memory is really scarce. In this case, direct reclaim cannot help. Background applications will be killed to reclaim space. As a heavy cost reclaim scheme, systems should avoid it to be triggered. According to these results, direct reclaim is often triggered. According to the report, servers also have the same problems. But on mobile devices, there is an opportunity to solve this problem because there are characteristics. Okay, let's see the characteristics of mobile devices. The first one is that the allocation size of mobile devices are usually small. Thus, compared to the allocation size, reclaim size is often too large. First, let's see the distribution of allocation size. We evaluate the size percentage when using different applications. The color represents different size. The size of order n is 2 to the power of n. We can see 99% of allocation size are 1 page. This is because more requests to mobile applications are small in size. Then let's see the distribution of reclaim size. The 80% of reclaim size are larger than 32 pages. And we found that large size reclaim is often conducted by background reclaim scheme. In a word, the reclaim size of background reclaim is often too large. The second characteristic, foreground applications are more important to user experience on mobile devices. However, we found background applications are still active, and background applications keep consuming free pages. There are two reasons. First, anonymous pages from background applications thrash file pages of foreground applications. This is because anonymous pages are more important to a process than file pages. Second, applications are still active in background, even though after 30 minutes. In this figure, a large percentage revolts are induced by background applications in blue. How to solve these problems? Based on the above analysis, we know there are two goals for memory reclaim scheme on Android mobile devices. Thus, we propose Acclaim foreground-aware and size-sensitive reclaim scheme. It includes two parts, which target the above two problems respectively. A lightweight prediction-based reclaim scheme, LWP, targets the first problem. Reclaim size of background reclaim is too large. It solves this problem by dynamically tuning size and amount of background reclaims according to the predicted allocation workloads. Foreground-aware eviction targets the second problem. Background applications thrash the pages of foreground applications. It solves this problem by relocating free space of background applications to the foreground applications. Let's see more details of these two schemes. LWP consists of two parts, a lightweight predictor and a moderator. As framework is shown in the figure, we use a sliding window to implement a predictor. To reduce memory overhead, the sampled allocation requests as input are stored in the predictor. The outputs of the predictor are the predicted reclaim size and the trend of reclaim amount. And then the moderator tunes the size and the amount of background reclaim according to the predicted reclaim size and amount trend. Let's look at an example. Predicted size and the average of size in window. Predicted amount trend is sum over last sum. To further reduce the overhead, the sliding window is lock-free. Let's look at this figure. There are 3 usage cases. Launch and use Chrome. Launch and use YouTube. Launch 5 applications. Take Chrome as an example. X-axis is the time. Y-axis is the log of sum of reclaim size in a sliding window. The green line is the value calculated by the original allocation request. The blue line is calculated by the log-free allocation request. And the yellow line is calculated by log-free and sampled requests. We add the vertical red line to denote the amount trend. These results show that log-free and sampling case capture the same trend as the original case. By this way, LWP dynamically tunes size and amount of background reclaims according to the predicted allocation workloads. Let's see the framework for FAE. FAE needs to know whether a page belongs to background applications. To reduce delivery overhead, we use a config file to store all UIDs of user applications. When an application is stored or upgraded, the config file will be also updated. When users switch applications, the UID of foreground applications will be delivered to kernel, and then background applications can be obtained by subtracting the foreground applications from all applications. In the eviction procedure, these background applications will get lower priority when they are moving. For example, when a page in active list is referenced, it should be moved to the header for active list, but if it belongs to a background applications, it will be moved to the header for inactive list. It's same in the inactive list. So FAE can extract space from background applications and allocate it to foreground applications, and thus reduce foreground page reforce. Notably, music and video players can be excluded in background applications, and thus their priority will not be lowered. We evaluate a claim in several aspects. For example, we show the read and write performance under intensive request by writing or reading half or 1 GB of data. The results show that Acclaim improved write performance by up to 49%. The read performance is only improved slightly, as the latency for page allocation is only a small part of read latency in this set of test case, because there's no dirty pages are generated. Thus, we can conclude that Acclaim can much improve the performance under intensive requests. We also evaluated the benefit to user experience in application launch. The results show that Acclaim outperforms the baseline in most cases. It benefits most application launchings. More additional results in our paper. We do not mention them in this talk. Let's look at the overhead of Acclaim. For memory overhead, FAE needs to add a UID for each page. The UID takes an integer. Thus, a maximum overhead is 0.1% of memory capacity. Moreover, when there are 100 values in sliding window, LWP will take up 400 bytes of memory. For performance overhead, FAE only needs few comparisons, and LWP has 2 parts of overhead: lock-free sliding window, and it could prolong the wake-up time of background reclaim. Based on this data, both memory overhead and performance overhead are trivial. Now let's conclude this work. We found the memory reclaim scheme as inefficient in Android systems, especially under intensive I/O requests. Because there are many page defaults and direct reclaims during application daily usage. This work aims to improve user experience under intensive I/O requests. The work name is Acclaim. It includes two parts, a lightweight prediction-based reclaim scheme and a foreground-aware eviction. LWP dynamically tunes the size and amount of reclaim scheme according to the predicted allocation workloads. FAE sees free pages from background applications and allocates them to foreground applications. Experimental results show that Acclaim can significantly reduce launch latency and improve read performance under intensive I/O requests. That's all. If you are interested in our work, please download our paper by scanning the QR code. Thank you for listening.